All right, so this is lecture 12, Municipal Waste Management. From now on, we'll not discuss anything about hazardous waste. At least the materials will be mostly on municipal waste, means waste that we produce. The very first homeworks we have, I asked you to check what kind of um, waste that you guys found. The TA has already made a list of things, so we'll share the data with you based on how many, what kind of stuff we find always in our, and it was pretty obvious, most of them are food waste, plastics, or paper. They're not much. There is nothing unusual, or there is nothing on. It's a very similar percentage as what we found in the typical municipal waste. Um, so this announcement, quiz 3 is today. Today means I'll release today around 9 p.m. Um, but I encourage you to, we'll discuss a little bit about the previous, the lectures that related to this quiz so that you know what to read. So if you have to take the quiz, take it after you read all that. Okay, so don't be rushed. Take it tomorrow. You have 24 hours, so it's only 20 minutes. Project outlines have been meeting continuously with different groups. So just send me emails anytime you wanted to meet. Again, it's not like you have to write something for me to meet with you. We just want to discuss like how you discuss with any other office hour. So treat those times as office hour. But we have dedicated office hour on Monday 2 to 3 p.m. So next week office hour, I'm pretty sure this will be busy because of midterms on Tuesday, or release. It will be released on Tuesday after the class. Again, it's 2-hour midterms, but you have 1 extra hour for uploading and all that stuff. There will be 3 questions, long questions, and 2 to 3 questions, long questions, similar to homework, and 1 question will be multiple choice questions, like how you do have in midterms, in quiz. The difference between quiz and those questions, there you have to explain it. That way, when you get it wrong, you'll still get credits for explaining the reason behind it. Again, the quiz, the midterms is between from lecture 1 to lecture 10. We have midterm review last class, so you should watch that if you didn't get a chance, or if you didn't attend the class. And quiz 3, let me just quickly go through quiz, what you are going to look for. Again, 8, 9, 10. 8 is bioremediation. So I'm just going to go to the bioremediation slide so that you see what those are, things we are looking for. Okay, so these are the annotated slide. You can check. Okay. All right, so lecture 8. These are not, no, this is an important slide. Okay, this explains about what kind of pollutants you can remove in aerobic versus anaerobic. So one of the questions in the last midterms was related to how to change chlorinated solvent. It doesn't require oxygen, or oxygen, it is anaerobic. That means you don't need oxygen. So think of these slides as one of questions. Same thing, this slide is also important. This tells you about which type of pollutants, organic pollutants, will be difficult to degrade. So that's the reason given here. Branch 1 will be difficult to remove. Chlorinated, fluorinated, all these solvents are all, these functional groups are difficult to degrade because they are highly electronegative. And also bioavailability. Bioavailability means, if it is bioavailable, then can they degrade. If it's not available, they can't access to it. So these example quiz questions are here, so you could check that. Okay. This is the same. This is more explanation about chlorinated or fluorinated compound. What's the reason behind this require reductions or no oxygen? So it's there. Then all these slides over here, I'm not going to ask questions on difference between different types of treatment. This is more of your learning experience. Okay, this is not something I'll ask in quiz. This is more like a specific stuff. Okay, Um, check this one, this slides, disadvantage, disadvantage, what could not, where you cannot have bioremediations, where it is less efficient. So this is also important slides. Design calculation, as again, you need to know how to solve these questions, right? So if you know how to solve these questions, you might also understand why these are important. So I'll not ask a lot questions where this will be, you have to calculate something. For at least in the quiz, in the midterms, I ask calculations, short questions. Okay, but here at least you should know the concept. For instance, here the required volume, how you increase the how what are the different factors that affects the required volume, amount of water needed. Okay, so for instance, if I ask this questions, originally the soil is highly wetted, how much do you need, more water or less water? If you see this difference, the SI, that's the initial saturations. If you already have highly water saturated, you don't need much water. So you can both think of this as conceptually as well equations. So anytime you see equation, stop there and think of it conceptually. Okay, and not just thinking of that conceptually. Think of everything else. What can change that? For instance, it says volume of soil. What can change the volume of soil? If you have larger area, that will increase the volume of soil. The second one is porosity. What can change the porosity? Porosity can be changed if you have different particle size. Porosity can change if you have compactions. So you have to think of all that too. So what does, because that's the only way you can also think how this will influence indirectly the amount of water needed. Okay. Um, this is again question you should think of. What is the concept behind it? You need more carbon than nitrogen. You need more nitrogen than phosphorus, and all the calculation behind it, so that you at least know the concept. So literally you have 4 or 5 slides here in this bioremediations to think of for the quiz. Phytoremediations. So let's go back to the phytoremediations. Okay, that's never ending. Okay, so right. So this is just from previous. Okay, so phytoremediation, just think of, these are all concept questions, so there are no calculation here. You should know now the principle behind all that. For instance, if you see phytostabilizations, it occurs after the roots, outside the root, it doesn't occur inside. And then think of, phytoremediation, all the difference between those for stuff. Okay, so if you know how it works, then you know what can influence it. For instance, as I said, it's written all there. The pH is written here, all that factor. So you should think of those at least now. What is happening inside or outside? What condition influence those? For instance, anything related to roots, root distance, how far it is from the root is going to influence those. So if I ask, what are the different mechanisms that are influenced by root, you will tell, root length, then you can tell which one. Okay. So this is just an example of just the concept, broadly concept, not necessarily too deeper. Not this is just example. Uh, this is example. Um, so this could be one thing to check. You can see that what are the elements that can be removed by phytoremediations. Okay, there are some elements that can be, so you should see those here. But usually I don't ask anything that you have to memorize a lot. Okay, something you can think of. Okay, these are just these are okay criteria. Nothing here, there is no cost, nothing conceptual here about it. Um, so you should look for this one: advantage, disadvantage. What makes the bioremediation less effective versus more effective? So at least you should be able to compare phytoremediations with other technology based on this. Design calculations. This is one equation. Anytime you have equation, you have a potential question there. So think of that as a how uptake rate is influenced by different factors and what controls those factors. Okay, that way you'll be able to um, think of that. For instance, transpiration rate of vegetation. So think of what transpiration rate means. It means how much water it can be pumped and it pass through the leaves. So what controls that? It controls by the leaves. So if you have enough leaves, it will pump more water because that's the exit route. If you don't have leaves, they will not pump out that much water. In fact, that's the reason if you see winter conditions, most of the trees they lose the leaves because they don't want to dehydrate. Okay, they don't want to. Not moisture is not enough available, so that's the protection strategy. So at least think of those in general, like a conceptualize. Okay, not too much details. This is one again equation. You should be able to think of that just by looking at the equations. So there are two equations, that's all, so there's not much here. The last one is nanoremediation. So I'm just going to go through beginning. All right, so I mean, this is just a simple thought. There is nothing there to think of. It's just a size is nano. There is one question here, how the surface area changes, the reactivity, all that. So, but not much, simple question. This is, I'm not going to ask you anything to memorize here, okay? These are just for your information. The equation, for instance, here, the nanoparticles, just concept is size makes a big difference. Smaller the size, more reaction it is. And there are certain things like silver. It's not that silver smaller size is toxic. It's more about silver dissolve. And just because small size, the reaction become more. So that means it can dissolve much faster. Or too small silver can also penetrate into skin. So that way, once it's inside the skin, it can dissolve and kill. So there are different kind of reaction. It shows how zero valent iron work. Just look at the equation. It tells you what can controls it, what affects it. Okay, so I would look at this slide so that you know the understanding of that. So these questions are given, example questions, so you know what kind of question it should be. So this is just a concept here is that what affects the effectiveness of nanoremediations. If the idea of nanoremediation means it should be nano all the time. And you realize that now nanoparticles can aggregate because for different reasons. So that means if they aggregate, they become not nanoparticles, they become microparticles. That means their effective surface area is smaller. So they lose that advantage. So you got to think of how we can improve that. So those conditions are explained in the next. They're not there. They explain here. Okay. So I would say this is the important slide. Okay. So because here it explains how it can affect the reactivity or aggregations. So then it explained here. It explained that if you have too much ions, that can also reduce that repulsion and then it become aggregated. So your effectiveness will decrease if you have way too much salt or ions in the in water. So this is also that that more example of that. Again, this is a question. Just aggregation. What affects aggregations? This is all about this here reason. Okay, so this is a good slides, because all the conditions are given, how that affects it. Okay, so you should know how this is influence the nanoparticles reactivity or aggregations. That's it. So I think there is not much. Everything else is given. So literally you have 6 or 7 slides to think of in last 6 or 3 to 4 slides maximum per lectures. So think of those more, so that you know the conceptual. It should be okay. You should be able to answer because there are examples there. Any questions? Okay, so let me get to the today's lectures. So that's a quiz. Um, Now we should start discussing about municipal waste management. This is something when we start the class we talk about what the most common waste that you find in municipality. If you see, these are the common waste. By far, papers are the cardboard papers. Those are the most the in terms of volume. I'm not talking about weight here. This is volume based. And then the next one is mostly yard trimming. It's like you if you have a grass, all that stuffs, the trees you trim them so that you get some from there. And everything else, food scrap, plastic, glass, container, metals. These are the stuff you can see in the left side. The pictures, all those are there, but majority that you see over there are plastics. And there are, if I ask you the question, what are the two types of solid waste that were not there, or at least not the amount that we are seeing now in last 30 years? One would be plastic, another will be electronics. Okay, so plastics. Think of how many power cord or just connections to connect different device, your cell phone, your everything has this connection device. So that wire, everything has plastic. So these are there's so much. Before you didn't have that much. We the only electronic device we used to have is even the phone was connected and the landline. So you didn't have mobile that time. So there are way too many portable device now. So that means you have more plastic, more electronics, and they are related because no electronics is made of no steel, unless it's Apple product. Mostly it's plastic. Okay, so that means these are all correlated together. So today the class is mostly about those, and at least I'll give you overview of that, but not resource recovery aspect. Um, just want to say that look at this particular picture. And this is from probably India or Asia somewhere, and there are a lot of people are taking shower in this big rivers. And you can see for rituals or other things they do near the rivers, and they dump everything there. So this is just not just one country. There are many places. This is very common. So all our waterways are polluted with big plastics, and they are all exported to ocean. In fact, Asian country are the biggest exporter of plastic into oceans. Okay, um, and I'd also think that many of those plastics are not used there. Many plastic are actually also exported from European country to those country, and there is with the idea that they will recycle and produce plastic from them or create some other products. But many of them are 90% are usually is dumped back into ocean. So it's plastic pollution is a big issue. It's not within the geographical boundary. Once it's released to ocean, it's all in the big pool. So no one country can solve it. It requires a um, much bigger um, coordinated effort to solve it. Now, I don't know who are. I know that at least one project is on plastics. What are the health consequences of plastic? I didn't write anything here, but think of plastics are inert. That's the reason we are using it. If it is toxic, we'll never use it. Okay, well, some plastic used to release. Uh, I think if you see, some plastic used to release BPA, okay, bisphenol A. So that BPF all the time you can think of. A lot of times people make a label BPA free. Okay, BPA free means BPA is a potential carcinogen. So once it's found, BPA is something, it's not natural to plastic. It was added to make the plastic to have certain property. So once they find out BPA is carcinogen, they remove that ingredient. So that's why I have to think of plastics are not always, they're not toxic. Large size plastics are not toxic. That's why we are storing, if you buy milk from supermarket, you are buying in plastic. Okay, and you're buying many food in plastic, so it's not toxic. That's one point to think of. But once it becomes smaller size, it's very easy to eat them or engulf them. So what happened inside once they're in the stomach? Well, we don't know really. That. I mean, we are doing it every day. Every day we are inhaling plastic. Every day we are the moment you are entering that laundry room, you are drying your cloth, and then you are doing all this. Folding your cloth, you are inhaling plastics. Okay, because things will come out from them. So now, nobody knows. It's not nobody how much toxicity it can be. So it's a very unknown field. We don't know much. We don't have much understanding. But what we know that is the amount of plastic that will be in the nature is going to increase exponentially with time. And it has been. So now that you have so much of plastic and we don't know what is causing, we'll soon find out once people are doing research. And so EPA, DOE, they're all now interested in how to make alternative use of plastic. Can we upcycle plastic? Can we one instance is plastic is basically a polymer. So that's something you probably see earlier. This is basically a polymer, organic polymers. They are polyethylene. Think of it, polyethylene. Means ethylene is organic molecules. Polyethylene means you have multiple ethylene combined together, like that polymeric chain, right? So this is at the very basic form. It's an organic bond. Okay, it's very difficult to degrade because of that polymeric chain. So, but it's not really pollutant, it's a basically hydrocarbon. And so that means there are ways to we synthesize them from a small molecule. So must be there is a way to break it them to something else that can be used for other product. So there are multiple applications. Plastics are used for road applications. Plastics are used as a um, to build roads. Plastics are used to produce energy by thermal decompositions. You burn them, but then it also produces toxic gas. So that's why it's not being used as much in that energy productions. But now people have begun to find out all that. So if you are picking up this as a project, there are way a lot of opportunities to think about, and you are actually doing research on something that will be in next 10 years. So this is just to show that per capita generations has been increasing, and the total amount of municipal solid waste (MSW) has been increasing with time. This is including plastic and everything else. And the amount of recycling has not initially it was increasing a lot, but now the recycling rate is actually kind of the slowest. The reason is it turned out recycling is always depends on how expensive it is to get the newer materials. It's easier to recycle if the or it's more economical to recycle if the cost of that product is very expensive. Okay, it's hard to find. So there is no incentive for recycling something if they're much easier you can buy for few cents. So that's one of the reasons our recycling rate has decreased over time. So it's time to think of instead of recycling, maybe we need a different kind of way where we can change one product to another. So I'm going to give you just simple examples. Every day we use paper. Paper is one of the biggest waste that we produce. And if you think of what's the impact of paper, every time we we use paper napkin, we just use and throw it. We don't even give a thought that much. But that one paper took so much, if you think of carbon footprint, is humongous. Not only we cut a tree, but also papers are not produced locally. They are produced at one central facility. So that means it has transportation cost. It has it's a bulky material. So you have to store it somewhere. So that space, everything, if you think of every possible way, paper is the most wasteful product. Okay, and we use fraction of second and then it's done. So one of the video that I really loved it to watch. So let me see if I can copy and show it somewhere. So Okay, hold on, let me. Okay. Of content is not supported. I don't understand. Let's see. It's an interesting video. I want you to. Okay, for some reason it's not working. I'm going to put it in somewhere else. Let's see if I can. Okay, let me play in my computer. That way it's easier to watch. It's an interesting video. I want to emphasize it. Like it doesn't take much to save waste or recycle or manage waste. So let me stop the share now. It's a 4-minute video, so I'm going to share another screen. Okay. Okay, so let's see. Audio setting has okay, I'm just going to play from the computer. $571,230,000. Do I share my screen or we don't? I don't share the screen. Okay. 1,000 pounds of paper towels are used by Americans every year. If we could, correction, wrong figure, 13 billion used every year. If we could reduce the usage of paper towels, one paper towel per person per day, 571,230,000 pounds of paper not used. We could do that. Now, there are all kinds of paper towel dispensers. There's the trifold. People typically take 2 or 3. There's the one that cuts it that you have to tear off. People go 1, 2, 3, 4, tear. This much, right? There's the one that cuts itself. People go 1, 2, 3, 4. Or there's the same thing, but recycled paper. You have to get 5 of those because they're not as absorbent, of course. The fact is, you can do it all with one towel. The key, 2 words. This half of the room, your word is shake. Let's hear it. Shake. Louder. Shake. Your word is fold. Again. Fold. Really loud. Shake. Okay. Wet hands. Shake. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Why 12? 12 apostles, 12 tribes, 12 zodiac signs, 12 months. One I like the best. It's the biggest number with 1 syllable. Trifold. Fold. Dry. Cuts itself. Fold. The fold is important because it allows interstitial suspension. You don't have to remember that part, but trust me.
cuts itself. You know, the funny thing is, I get my hands drier than people do with 3 or 4 because they can't get in between the cracks. If you think this isn't as good, now, there's now a real fancy invention. It's the one where you wave your hand and it kicks it out. It's way too big a towel. Let me tell you a secret. If you're really quick, and I can prove this, this is half a towel from the dispenser in this building. How? As soon as it starts, you just tear it off. It's smart enough to stop, and you get half a towel. Now let's all say it together. Shake, fold. You will for the rest of your life remember those words every time you pick up a paper towel. And remember, 1 towel per person for 1 year, 571,230,000 pounds of paper. No small thing. And next year, toilet paper.
All right, so I guess this is a very powerful video because if you see, it doesn't take much for us to do change small. All it takes is a little change every day. So when we think of municipal waste, we should think of in that angle. That waste management doesn't have to be fancy technology. It could be just a little bit. All it takes is a little behavioral. Let me see why it's not able to. Let me hold on. Could not share the screen right now for some reason. Okay, now it's. Okay, so that's municipal waste. Now that's why it's important to manage that in a proper way. Then the second type of waste that comes is electronic waste. That's coming because right now we are using computer. This is one electronics. Right now on my desk, I have cell phone, I have a speaker, I have a computer. If you see how much of those, those are, and what's the average lifetime of them, realize there are humongous amount. So these pictures that shows just in Europe, this is the global amount of waste generated in 2016. That's 44, roughly 45 million metric tons. That is roughly 6.1 kilogram per inhabitants. That's mostly, think of that as a 12 pounds per person. And if you think of what that means, this is equivalent to roughly 4,500 fill towers that amount of waste that we are producing. And these electronic waste, think of how much energy it took for us to produce that. These are different stuffs, different elements. You do mining, humongous environmental impacts, for mining, and then you mine all that. You mine millions of billions of cubic soil to get very small quantity of these elements, and then you use those to produce all these electronics, and then you use it, and then you dump it. Okay, and these are all purified version of stuffs that come together, and then you just dump everything back. So that's why I think has to be a better way to deal with this. Instead of mining those, maybe you should start mining this waste itself and extract those rare earth elements, because the concentration of rare earth elements in your cell phone is way more than anywhere in natural you can find. It has also a lot of toxic material. So how to find and separate them is what the challenge is. And also to how to create a market for it. So that's why if you see there are different, if you think of different, it's very hard to see the screens. screen, the its resolution is low, but roughly the most amount, if you see the production of electronic waste, the contribution is from cell phone, because it's the smallest, the smaller size, the more frequent that you use contributes the most. Laptop computer is much lower than cell phone. For instance, if in 2010, roughly 50% of the electronic waste is from laptop, or the 50% of the percentage of adults that will produce the waste. And so where the electronic waste goes. So most of the time we think, these are coming, they are being all dumped into the into landfill, but most of for them, 90% of them goes to Asia. So all the cell phones that you throw right now is not really going to be here in any landfill in US. It's all going to Asia, some countries. So it's a, and what they do, the idea here was that an Asian country has the labor is cheap enough for them to extract and produce raw materials that can be sold again. So maybe there is a thought that you are producing economy, but it's not. The cost, the human health impact, everything is much higher. So there has to be a better way to manage it, and this is the way that is going on so far. You deliver the electronics, and then we use it, and we dump it, and then we dump it either in the recycle bin, if it is battery. If it is not battery, something else like plug, we dump it inside the regular waste. Then it sent to incinerator, where you burn it. And once you burn those, then you get this ash. This ash has a lot of these metals. Then it can be extracted, or it could be dumped into the landfill. And the third one is basically you ship it to another country, and those country can extract some materials and recycle it, or they could also burn it and create this toxic fume and all that stuff. So there is no win-win situation here, the way this is being produced or handled. So the future technology is more about extracting useful resource. If you think of what are the stuffs that electronic waste, most of them are plastics, heavy metals, and rare earth elements. The most expensive part, or the difficult one to extract, is rare earth elements. Plastic is cheap, so nobody want to extract plastic from electronic waste. Uh, so literally the rare earth elements is the most important stuffs in the electronic waste that could makes the economy feasible for this extraction process. Then you have also these fluorinated, brominated hydrocarbons, which are normally used in electronic waste so that it doesn't catch fire, because most of the cell phone get heat up, and that heat sometimes some cell phone can catch fire. So they have these chemicals, PFAS or other chemicals inside it to prevent accidental fire. So those are also you have to think of. So the traditional method, as I said, is a landfill. But now if you send it to somewhere else, then it can be combusted, and some of the ash can be used to metal recovery right here, and then rest of them will be disposed to a landfill. And the heat that you generate can also produce energy that can be used for electricity generations. But the biggest challenge for incineration is the gas that you produce, the toxic gas. And most of these are things done in Asian country. So the toxic gas is usually emitted into atmosphere. So anybody who living around those, they inhale those gas, so that's immediate danger. And then second, anything goes to air is also not going to be within geographical boundary. So this must be, there has to be a better way for this kind of process. Whereas alternative source can be really a high economy. So 55 billion zeros is the amount of money that can produce just by taking the materials. But it's misleading just to say that this is the amount of materials, because the cost of extraction is sometimes way a lot more expensive. So there has been research in US and UK, or not UK, Europe, to extract this rare earth element for long. And if any of you are thinking of this as a project, or you have One way to look for is how to use. The way it works is you have rare earth elements are basically metals. Okay, metals are dissolved when the pH is low. Okay, the acidic solutions. So you have to think of how where you can naturally find acidic solutions. Many microorganisms produce acid. Okay, so one such thing is, let's say, fungi. They can produce acid. That acid can dissolve metal. Okay, they dissolve metals and other things, right? So then you have the leachate. So all the landfill which has this electronic waste, if somehow we can dissolve them naturally, then you produce a leachate which may have high concentration of rare earth element. So one strategy here is that waste, electronic waste, that all can go to one landfill, where you could at least produce leachate by some kind of reaction, or you can add some energy some other ways, and somehow you can degrade them and produce a leachate that could have enriched in this metal. These are not developed yet. Now these are all things being considered. The other one is you can use microwave plasma remediation technology, which basically burning at high temperatures. So it just, the difference is so high temperature that you don't produce that intermediate toxic fume. Okay, you break it down to carbon dioxide, nothing else. Okay, because the incomplete burn is like when you break it down, that's where it produces the toxic fume, small carbon chain. But if you use very high temperature, imagine you throw the entire electronic waste into sun, hypothetically. Okay, imagine your plastic, it's big shuttle plastic, crash into sun. What will happen? The atomic, even the atomic level, it will break, right? It will become hydrogen, or it will become this individual atom, right? So individual atom is carbon and hydrogen. So that's the whole idea of this plasma technology. What it does, it creates the temperature that's right near the surface of sun. Okay, and so at high temperature, when you burn something, it doesn't break into the intermediate products. Okay, so the idea here is high temperatures. This is near sun. These produce um, intermediate toxic gas. So that means if you have plastic, low heat, toxic gas. If you have plastic, let's say greater than 10,000 degrees Celsius, that's the temperatures, then it produces CO2. Okay, so that way you have carbon dioxide, then that carbon dioxide can be captured other process, but then the idea that you get here is the rare earth elements. That could be, the inorganic will be always there as a ash, and then you can take those ash, and that's much higher concentration than anything on the earth as far as rare earth elements. But plasma technology is also high energy cost, right? So you have to think of all that. So this is, I already talked about the idea concept here, is that fungi or bacteria, these are organic, they produce organic acid. And then if you have electronic waste, so that means the H plus ions, if you have way a lot of H plus ion, that's what it does, acid. Okay, the rare earth elements will leach out from the waste. and that way you can harvest them, or this goes to leachate, and then you can extract those rare earth elements from the system. Um, so let's say imagine this is your project. What kind of different things you should discuss? You should discuss about source reductions. Like I said, paper towel technology. What kind of things you do. So instead of buying a cell phone, or buy a charger, instead of buying a wire charger, buy the wireless charger. That way, that you don't have to keep buying um, the that wire all the time. So wireless is one technology that would eliminate that. Same thing, there are different ways you can think of everything you use, how we can minimize that or increase the lifetime of that. For instance, as I told you, like every agency now start, every electronics producer trying to make the same kind of outlet, USB-C, so that way there'll be less amount of electronic waste. So this is just one way of source reductions. So think of many possible way. Even UCLA, if you think of UCLA, they in many computer lab, the perfectly good computers, what they are doing is they are replacing every few years. So to think of, that's also a wasteful way. That could be donated to somewhere, or it can be reused. Those are other one thing. Second is recycling. Instead of throwing it, Apple does that. Now there is a reason they give you some money when you recycle the phone, because they have aluminum. All the phones are pure aluminum. Those are expensive, high quality aluminum. So for them to extract that aluminum is much more expensive. So that's why they're paying you back that money that they would have invested there. So it's a good method. So that means they should design the system such a way that it's easy to break them into their raw materials. Composting is another technology which is basically letting them grow in fungi or microorganisms which produce high energy, high amount of or acidophilic bacteria. So that means it can survive at high um, low pH. Then you have to think of management of transportations, because that will also produce more waste or carbon dioxide. And so again, there are two form of technology. You can use landfill or energy recovery. So landfill is basically, we are going to cover in the second half. The energy recovery is which already discussed. We burn them and you get some energy out of it, and then you also recover that waste. All right, so we'll take a break for 10 minutes um, until 5:05. Then we'll be back. We'll discuss about landfill designs. How when you dump in landfill, what are how you can recover some energy from that. Okay, so I'm going to stop recording. Right. So now we are going to learn about the basic principle of landfill design, and what are the different component of landfill. How do you know when the landfill is not appropriate for certain waste, and what kind of waste should be sent to what kind of landfill? These are the questions you should be able to understand by end of this class. And this is the links that you should go. If you go to EPS sites and click landfills, you should be able to see many of them that we are going to discuss now. So you don't need a textbook for this. So now landfill is the most ancient technology. Okay, before, the only way we manage waste is we dig a big hole and we dump everything inside, bury them. That's how we create. That's how we manage waste historically for last within 100 years. Okay, so and only in last few years, or last 70 or 80, 90 years, we realized that just by dumping them in the waste underground doesn't mean that you are getting rid of it. Stuffs will come out. In fact, there are gas, there are liquids, all those things can source up. So that's why now landfills are evolved to design different way. And so these are the four functions that we try to do in the modern landfill. Number one, whatever the waste you expose there should not come out again. Okay, so that's the first one. Number two, even the waste doesn't come out, it's going to produce leachate because there will be moisture penetrate into it during landfill use, and those leachates will have stuffs, chemicals, all the things that could leach out of those materials. So you got to manage the leachate so that you can protect the groundwater. So if you have landfill here, this let's say landfill, first is um, the boundary should be um, containment. So this is mostly containment of waste. Okay, and then the leachate, which can have many pollutants, will go to groundwater. So that means you got to have management. You don't want leachate to go to groundwater. That's number one. Then it can also, if it is a lot of organic, it produce methane gas. Okay, and so you got to capture methane gas, otherwise because it's a greenhouse gas. And not just because it's a greenhouse gas, because you have ability to capture it, you are losing money by energy source here. If you burn that energy, if you get that methane, you can actually produce electricity. So that's why it's important to capture it, as well as reducing the greenhouse gas emission. And the last concept, which is not always needed, is to degrade the pollutants. Because the reason you dump things in landfill so that you don't really care, you don't really have to worry about. That's why hazardous waste are being dumped. But there are now provisions where we could actually think of destroying the pollutant or degrading the pollutant or waste so that you can produce leachate which are useful. So mostly this is related to recovery of materials. Materials are the um, raw materials. So for instance, rare earth elements, metals or precious metals. In fact, somebody says that the amount of gold used in the electronic waste can give you more gold than a gold mine, or if you are looking for gold somewhere in the random place. Okay, so this is the landfill look like. This is how it should look like. It's a land. You dig the soil, create a big hole, and you create different layers so that you minimize that leachate. So this is the leachate management. You have to design layers to minimize that, and you have to top layer to minimize the gas emissions. Everything else is a simple concept. So, and different designs, we'll discuss that what the difference are. Just know that now these are your waste. Okay. There are different types of landfill. This is something got to remember. Type C, type D. So those are RCRA is the Resource Recovery Amendment, or not amendment, act, um, that define what is hazardous waste. So type C means hazardous waste. Type D means solid waste or municipal waste. So the design of landfill, the permit, it depends on the type of waste it can receive. One type of design cannot receive another waste, right? So it's very important to define that very early. So there are three different kind of design. Obviously, municipal solid waste that we'll discuss much more, or relevant for our class because we are going to discuss about the energy generations. But then other two type of waste that we don't discuss that much is industrial waste. Industrial waste is basically construction debris, where it could be also industrial production site uh, like ash, okay, coal ash. And the hazardous waste, it's pretty clear, all the hazardous that we produce, they dump it there. And so the design will be more stringent for hazardous waste. So that's the whole reason it is there. So anytime you have to define waste, the landfill design, you have to think of all these factors. So let's go through one by one. Number one is waste type, because that will decide what kind of design it has to be. Again, the more hazardous waste, the more stringent design, that means your liner has to be much more stringent. There are multi-layer liner items to prevent those leachate to go to groundwater. And then second thing is your location restrictions. You cannot produce or you cannot create landfill in a location where you compromise the landfill by anyway. For instance, if there is a location which is the earthquake happens multiple times, you cannot produce or you cannot create landfill there because it will open up at some point. And then you cannot also make landfill near the waterways like rivers or wetlands or any natural water systems or above the groundwater, at least where the aquifer is permeable. So these are the reason. The reason is you want to protect your water resource. Um, so that's the second one. Well, you may not have choices many places. If you don't have that choice, you have to make sure that you create this composite liner, which is basically impermeable membrane, so that no leachate will pass through it. Okay, so that's the third one. Then the fourth one, again, if you don't have a leachate collection system, things build up and then it will leak. The pressure will build up. So that's why you have to collect leachate. And second, leachate collection is a good strategy to prevent groundwater contaminations. Because if you remove all the leachate, there is no force or gradients. Or if you build up water, then there will be high pressure, and then things will start percolating into ground. Because if you remember hydraulic conductivity or the Darcy's law, amount of water that can infiltrate into any porous media depends on the hydraulic head, which is basically how much water lying on the top of the soil. So if you remove that leachate, that takes away that head or takes away that pressure. And then also leachate recovery is part of resource recovery. It's not just you are lowering the chance of groundwater pollutions, you are also increasing the um, probability that you'll also extract some resource out of it based on what kind of waste you have. Then the third one, these are last three one is more about monitoring. You how you operate, how much inch of soil you should add after every layer of uh, waste, because that's required for compactions and that require for how much moisture you need to add. And so all those operation practice will help understand and the pollutions like smell and all that other factors. Groundwater monitoring and all the other post treatments is needed. Construction waste, this is just the simplest type of landfill is construction waste, demolition waste, because you really have metals and concrete. And those goes to a simpler one. It doesn't have much really pollutions from it. But again, the same thing, you still don't have to use it near the waterways. Industrial waste, this is just one example, just to show that how it is being produced or built. This is near a coal power plant. So you see, this is a geosynthetic membrane. They put it here. This is the membrane, and they have also below it there are clay. This is clay, and then you have a membrane, and then we'll put more membrane or clay materials before they dump um, all these colas. So this is a colas. Okay, so then the last one is hazardous waste landfill. The example would be the solvent. It could be also nuclear hazardous waste. We don't really make landfill like this. It is much deeper reservation. So that's like below even groundwater levels, below a lot below groundwater. So that no earthquake can move them up. But this is just regular hazardous waste. And the key here is that you are going to protect it the bottom layer a lot more. So that's why it has a double liner. Okay, everything you can think of, everything twice. You have to do twice because just to be extra precaution. Not only that, you have to be to prevent Everything that's done around the design is one based on one simple logic. How do you minimize leachate? Okay, there are three ways to minimize leachate. First, you prevent any water to get into it. So that's the number one here. So this is runoff reductions and all that stuff. And then you have to also leak proof them. Means you put double liner and you collect leachate more frequently than other. That's why you have two double leachate collection system, so that in one the chance of failure is low, and everything else is very similar process, and your cover will be more stringent so that the waste will not be released. Again, go back to these links if you want to learn more about it for your project. So now that we learn all that factors, now what are the different things we know now for landfill? These are the things you'll think of for your project. What kind of waste? Okay, and how do you manage the stuff that come out of here? That's gas. That's also leachate. I know one of the group is working on food waste. This is something you can think of, but again, that's for much larger scale. But if you are looking for food waste in the smaller amount, then you can think of another technology, which is anaerobic digester. We'll discuss that in next class. Um, but that's a similar principle. You produce methane gas out of organic waste, and then you minimize the leachate or the manage it by controlling the amount of water that get into the system. Okay, so that's basically the dry containments, all that liner technology. And then you have to think of make sure that it's not placed anywhere which can pollute groundwater or any surface water. And then other things to consider is energy. How much energy are the required to collect waste? Because you don't want to put also landfill so far away that you have to produce this. It's too far away from a city, so that it takes a lot of energy for them to dump truck to drive there. So that's another thing. And other locations, as I said, soil type, it has to be on the clay soil. So anytime you have to think of uh, the any land which has high clay content is a great place for landfill, because that naturally doesn't have high infiltrations, because K is lowest. Then also you want to make landfill at locations which has a dry area, doesn't have flooding. So that's why Los Angeles is a great place. A lot of landfill around here because of dry climate. But if you receive a lot of rain, you don't have a choice, but you have to also account for that because you are naturally getting so much water. So maybe, if it is too much, then you put landfill in a location which doesn't get flooding easily. And then you have to think of all the groundwater directions and all that other security that's written here. Again, that I'll, I'll share a handout so that you can see more if you need it. So this is one slide that's most important when it comes to quiz for the next last quiz, is about function of different layer. So we cover that in the in CE153. I'll just everything is written here, so you can read it later. But I just want to explain the basic concept. So let's start with this. 7, 8. 8's at the waste. That's the main thing, right? This is all it cares. You have to put waste inside it. The very first thing you have to do is making sure that they are compacted, right? So that's the first function. When you are putting waste there, you are rolling them on it so that it's really compressed. And then there is one thing you can find here. There is a cover here, number 7. What could be the reason behind it? Because you can just mix all the waste at the same time. If you realize what that number is, it's called daily cover. The reason why you have to daily cover that one is because of the gas, the smell, as well as um, that helps you also compact it, because you cannot really drive on a waste directly. You have to create some kind of a layer of soil so that you can, when you drive on it, it's just compressed. And these landfills are actually much longer area, so you cannot just dump on the waste and drive on the waste. So they dump all this waste and make a soil layer so that they can drive on it and to dump it little further and further. And the process also they block any kind of smell coming out of it, and same time also the um, the any kind of wind erosions, because these waste can be um, wind blown, right? So that's why this is a critical strategy for that. And third thing also, it prevents some kind of percolation of, if it is a high amount of rain, you can also protect that. Okay, so that's the function of number 7. So you got to remember all these functions. So now let's go up, go down from there. So for the very first thing you worry about when you put the all this stuff is what happens to those waste. It will degrade, decompose, leachate will come out. So your goal is to collect leachate. So as you see over here, the way we collect leachate is number 11. Okay, that's the collection of leachate. And there's the pipe, PVC pipe. So that's the where the liquid comes out. But as you see around 11, what you have is gravel. The reason you use gravel is because you want the things to collect very easily. You don't want low hydraulic conductivity. You want the water to percolate very quickly. Okay, so that's why the gravel is there, and it's also sturdy. So that means it will be protected. There will be not much displacement. And then above gravel layer, you can see number 10. Number 10 is basically a liner, or perforated plastic liner, so that it can allow stop to come in, but it should not let the soil fall in, because if the soil will fall inside, the material inside, it will clog the gravel. That means you cannot collect the leachate. So look at all those instructions there so that you can read what exactly it is there. Um, so this is basically just the filter just textile to remove any kind of stuff to come into solid particle to fall into the system. Then on top of that, you see this number. What is that? Number 9. If you see number nine is basically that's where everything from the west will fall into that, right? So that's a layer of sand and gravel and all that over here. That's basically sand. So the K has to be high enough to allow water to percolate, to infiltrate. So basically sand there. Um, you don't put just the gravel there because the sand is easier to filter through a lot of debris. Okay, and so you that way protect the gravel layer. So look at all those, and then at the bottom is all about minimizing the leachate getting into groundwater. So you have one big plastic synthetic layer. That's number. So this is the you can see there's a those are basically the plastic tarp that you see. Okay, and then number 13 is basically clay, compacted clay. Those clay will have like very small porosity, high porosity, but this is so small particle. Hydraulic conductivity is way small. Like it takes years and years to even pass through a few centimeters or inch. So that means the idea here is that for any water to move from here to here, it will take, let's say, 500 years. That's the whole idea of having that compacted clay. And then above, once you finish the landfill, you do the exact same process. You put back the clay over on the top, put another liner, and then on top of that, you have soil and you grow plants. The reason you want to grow plants is for aesthetic reason. This is after you finish the entire reclamation of land. So that means landfill is the bottom. You want to have normal soil and then growth medium so that you can have a grass, because if you don't put any kind of plants, the erosion can happen. Every time there's a rainfall, the soil will wash out, that will expose the clay, then things will eventually will be eroded out. So that's the reason you have this soil and other aspect of it. And as you see, they are also percolated rare, so that means you have way to collect the leachate or the runoff, because things will lead. You don't want all those to get into the landfill. So read all that in your and so that you can prepare for the quiz for the next one. So I'm going to. The question is here now. You can see the questions are very similar to this kind of question. I just say that this is just one. Each one is one question. So for instance, if the question was to limit waste exposure to environment, which are the layers? So when you think of environment, it's not just the up, it also down. So let's see now how many of you can, which layer you'll answer. To limit waste exposure to environment. What are the different layers? Number one, let me say that number 6, that's the clay, top and bottom. What are the other layers? Prevent exposure. Think of, one is the clay, another is um, or the synthetic layer. No? So number 12. If I ask, then many other you can choose. So let's see, there is a chart window. Yeah, let's say number 13. 13 is, yes, 13 and 6 are same thing. And number 7, let's see, where is 7? So 7 is, yes, now if it's the wind erosion, but if you want the landfill is designed, then it's not the sorting of functions. So to limit leachate and leaking, which are the layers? That's when you talk about leachate, it's always down. So that's number 13, 14, 12, all those. To capture gas, it has to go to the top. Okay, so to the capture gas, it has to be captured from here, right? Because it will pass through all the lake will go there. Okay, so the final thing before in the class is landfill design calculation, how quickly it will degrade. The very first thing you have to think of, this is no new concept. Always we assume this is first order reactions. The microorganism is naturally present, they will degrade in the first order. K is the first order decay constants. And only concept you have to remember here that that constant depends on temperatures. So if you have higher temperature, it degrades faster. So that means how do you increase the temperature inside the landfill? There has to be some recirculation system where you inject warm water so that it can increase the temperature. So this is just the example to show that. Okay, so how do you apply the real world problems now? The temperature, basically that's what I said now. You apply the warm water because you produce methane gas, you can heat up that same water and recirculate it. So now let's have example quiz question. Biogas production in landfill is greater in which season? So the difference between winter and summer is temperatures. Then you have to use that as a way to understand when the biogas production will happen, more higher amount. And biogas production, as I said, is a biological process and which is required. All right, so most of you have a few seconds, 5 more seconds to answer. If you have not, I'm going to end the poll now. Yeah, this is perfect answer. So as you see, all of you, 100% say summer. The reason is it's a biological process. It requires high temperature. Second calculation is about how long before you have to worry about the leachate is going to leak. Okay. So as you see, this layer is all of clay. So the question is how you answer that is all about hydraulic conductivity and Darcy's law. So if you see Darcy's law here, that's already we know Darcy's law is velocity permeable, the velocity of Darcy's velocity is um, dH over dl um, of the length. Usually for vertical directions, dH over dl is usually for 1 for vertical transport in saturated layer. The idea is your head will drop the same amount as the water moves because it's the height will exactly same as your distance moving. So dl is dh are same, so that's why it's nearly 1. So that means Darcy's velocity will be hydraulic conductivity of the medium. Um, okay, so um, then velocity of water is you have to consider porosity. So that's velocity of Darcy's law divide Darcy's velocity by porosity, and you divide that into divide that in okay. So I is here this one. You put all this value, you get the answer. So let's calculate this value. The clay liner has a depth of 1 feet, which is compacted to lower its porosity to 0.5. Normally, clay has a porosity around 70% of clay's pores. So it's compacted to 0.5. How many years would it take for the leachate to migrate across the clay layer? Assume that the clay liner is saturated with a ponding of 1 feet above it. Okay. So your clay liner here and your water is here. Okay, so this is clay. 1 feet above water. Saturated with the bonding 1 feet above, and K is given. This K is 10 to minus 10 feet per second. So if you calculate the time is basically distance, where the distance 1 feet by velocity of water. And velocity of water is Darcy's velocity by porosity. Darcy's velocity is Ki by porosity, so the porosity will go up. So that's dN times Ki. So this is 1 feet. Porosity is 0.5. K is minus 10 feet per second. And I, again, it's a vertical transport. So that means, if you think of the dH over di, so that will be equal to 1. And if you calculate that also, it will be, you can find that. Let's say A and B. Your water is moving from here to here. Let's calculate that dH. Head here at A is 1 feet. Okay, this is 1 feet height. So head at B gives width plus that extra height. Okay, so that would be the amount of water above it. So that will be 1 plus 1. So that's 2 feet. And at A, this is the height of water above it is only 1 feet. And if you think of the distance between B and A is 1 feet. So that is 1 feet divided by 1 feet is equal to 1. So anytime vertical transport, you can assume this is 1. So that should be fine. So the number would be 0.5 times. So this will 5 times 10 to the power 9. 5 billion second. Okay. And if you divide that, let's say how much is 1 second in terms of year? 1 year second. That will be 3.154 times 10 to the 7 is second is 1 year. So let's say this is 3 or 5 even. So that means it's almost, if I divide that, that will be 500 divided by 3.154 year. So that will be how much? 158 years. Okay. So as you see, this is a long time. Okay, so that means what it means that if you have 1 feet of soil water above it, it will push that there. So that's the one of the reason you can remove that leachate so that you can increase the time to even longer. So that's why if you see, most of the time they don't allow the water to build up above certain height. And so that H max over here is the amount of maximum things you need to have. So that's the whole idea of the liner design and how much you can drain or when you can drain. So this equation is there. I'm not going to discuss that. Just know that it depends on the transmittivity, which is basically same as how much water it can pass through within time. So those are here now. We don't need to discuss that more. But these are equations just to show that leachate to gas, you can use Henry gas constants to measure the concentration of amount of pollutant in atmosphere or the gas if you know the liquid. And you can use diffusion equation, Fick's law. These are again, we are not going to use it. Just know that this is how we can calculate how much it can permeate through the system if you're looking for the gas permeations. The last thing is what kind of stuff will leach. Assume that leachate is coming out. That depends on diffusivity, and this is one of the quiz question will be in the final other in the other things is there are different kind of ions. You already know the hydration sphere. You go back to the same thing. Whichever has the highest hydration sphere, that means they are not going to interact with all these materials. So that means they are not going to stick around. So that means they are the one which is going to leach into the system faster. So if you see lead is the biggest atom. It has that's why it doesn't have much hydrogen, not hydrogen, warm molecule around it. So they are not going to be leached out. They will stick with all these soils and clay and everything else. Whereas sodium, which has the smaller atom, more hydrogen warm molecules around it, so they don't interact, leach out more likely. So this is just example given. Same thing for organic. Anything which is highly soluble, like alcohol, acid, they are going to leach out very quickly. Anything hydrocarbon, lots of carbons and not much functional group, they are going to stick around because they stick with the soil. So these examples are given here. So think of this one for quiz, this one for also quiz. And diffusivity again depends on the mass of the or the molecular weight of the substance. So if your molecular weight is high, obviously they are going to diffuse less. Okay. All right, so let's see if you can answer this one based on what we just learned. Which of the following species would be more permeable through geomembrane? Again, the one with the biggest hydration sphere will not interact. So magnesium versus beryllium, if you know, magnesium is the smaller atom, beryllium is the larger atom. Both have same charge. This is smaller atom. So that means you could understand now which one has highest hydration sphere, which one has the nucleus close to the outer cell. That means they can attract the more water molecules. If they attract more water molecules, obviously they will not interact as much with the other materials. So that means they will move faster. Okay, I'm going to close it in 5 seconds. Speak anything now, you learn from it. Okay, all right, so share the result. Which one of the following species would be more permeable through geomembrane? Again, more permeable means permeability depends on diffusion, depends on also reactivity. Okay. diffusion depends on mass, how heavy. If it is heavy, it doesn't diffuse. So that means beryllium is bigger, so that means that the diffusivity will be low. Okay, so beryllium diffusivity low. Let's say reactivity. Um, reactivity is depends on hydration. If the permeability increases, then reactivity has to be low. Okay, reactivity is low when the hydrosphere is more. Hydrogen sphere is more if atom size is small. That means the nucleus is close to the outer cell electron. So that means it is magnesium. Okay. So any possible way, diffusion increases if the mass decreases. So magnesium is also smaller. In both way, you can choose that more permeable would be this. Which of the following species would be least permeable through the membrane? So again, think of which one is more or least permeable. Least permeable means it will stick with everything. It doesn't have much solubility. Stick with mostly carbon because that's the one thing. Think of that what you learned before. So for sure, A is not a choice. I'll give you that answer first because that has OH. That means hydrogen bond. Hydrogen bond means soluble, water soluble. That means it's going to move. Okay. That means less sticky. Now you have a choice between these two. So think of what we discussed now. So I'm going to end the poll. Okay, so it's the result. Okay, so the answer is between B and C. Think of which has more carbon because more carbon will stick more. Okay, so this has more carbon, more adsorption. Okay, but if you think of diffusion, so this is one way. If you're thinking of diffusion, then diffusion you have to look at the molecular weight. But diffusion is not necessarily, um, the adsorption is the biggest hindrance why things doesn't get out of the system. Diffusion with time scales, everything diffuse. It just takes longer. So just look for more in the prospect of that way. So the answer would be C, because more adsorption. Okay, so the last thing I'm not going to do is just basically we'll discuss this more in the green infrastructure class. Is the outer layer. Outer layer is the soil membrane where you just have to ensure that you have enough soil and permeability so that you can have the plants grow, and plant will protect the membrane. The difference is you can see over here the soil, plant grow, the water will percolate, and then you have this membrane which will let the water flow out of the system. And you have some kind of gradient so that it doesn't um, stay in the system. That's all it is here. So now the question was, if that's the last quiz question, is identify the direction of gas and liquid movement in different layer. I see it already written. The liquid will go down, gas will go up. That's all. So that's what is written. Nothing. Okay, so the last thing I want to say is that if you want to remove liquids or limit liquid leachate, you fix the clay layer and geotextile layer at the bottom. If you have to protect the if you want to protect the if you transport them or collect the leachate, you put the gravel and all these pipes. Okay, so that's all for the landfill, and we're not going to go through resource recovery, which is here, because that's what we are going to discuss in the other classes. for anaerobic digester. It's the same concept. Okay, so that's all for the class today. And I just want to mention that quiz will be at after 9 o'clock. So I'll set the timer that way. So if you want to take a quiz early, then that's 9 o'clock is the earliest you can, and it will be open until tomorrow midnight. Okay, so that will be. Just gonna write it somewhere so that just in case somebody asks these questions, they can check here. Quiz somewhere. Okay, quiz release 9 p.m. up until 11:59 p.m. Friday. And it's 20 minutes, okay? All right, so I'm going to stop there. There was a question, I'm confused because this was on the diffusion of gas slide. Are there liquid or gases? Okay, so let me see. I just skimmed through it very quickly, so that's one of the reasons. The question was, identify the direction of gas and liquid movement in different layers. Well, if it is the arrow mark is given there, okay, so the liquid will only pass downward or sideways. It will not go up. That's the simple thing. And gas will move up and side. And it depends on what is on the upper. If you have a impermeable, let's say impermeable textile, then gas cannot penetrate. So it has to move to the side. So that's the only concept we have to think of there. But again, this is just the directions are all given already there. Just see whether there is any way for the water to move up or down. If not, then it will move sideways. It is liquid permeability. Yes, 43, slide number 43. Organic molecule. So it's a gas and liquid, both. It's written there gas permeability, but both can change. Heavier gas will not move faster. Okay, I'm going to stop recording now.